All right, guys, we're gonna get started. Um, so today we're going to continue, at least for a little while, with breaking RSA with that topic. So if you remember, I showed you how to use factor DB on Tuesday, and then another option that we have is to kind of use like a simulated quantum computer. So I'll show you guys today that idea. Okay, it's basically a Python library, but this is a very powerful. I think it was this library was created by IBM or something like that. So it's a pretty solid library. There's several out there. Since you guys have Anaconda already in your environment, you should be able to install this no problem. Just have to make sure we install the appropriate libraries. Okay, so that's the plan. I'll start with that. That won't take that long. I'm not going to go into any algorithms. This is not a quantum computing course, right? So I'm only going to show you this just to kind of tie in, since we're talking about breaking RSA. And then after that, we will install another library called PyCryptoDome. And this is a very important library that we're going to be using going forward. So this one is not about, so we've already covered a lot of like writing the algorithms from scratch. We will continue to do some of that, but now we're going to use libraries a little bit more so that we can focus on just encrypting things. And because as it's going to start getting more complicated as we have to achieve confidentiality, integrity, and authentication all in one shot. So there's going to be more involved. All right. So I'm recording the video here. Yeah. So what we need to do now is start the virtual machine. And I'm just going to give you the script. This is very simple. Since it's just a library, we're not implementing anything from scratch. I do believe the underlying algorithm that's being used is Shor's algorithm. So that's something that I always give students the option that if at the end of the semester you want to do a term project about Shor's algorithm, for instance, you can do that, right? But you would have to explain how it works a little bit, right? So obviously it's pretty complex given that it's quantum computing. So I'm not asking that you become an expert in that, but it's something to explore, a fun project. So those quantum, I think I've mentioned this, quantum related algorithms for cryptography are something that you can explore for the term project. We are on week 9, so actually you should start at this point. Even today, I would recommend that you form your groups, right? And you start thinking about the term project. So I can answer questions about that. But essentially, it's 10% of your grade, right? You can form groups of 2 to 3. So no more than 3, no less than 2, because you have to have some teamwork going on. And then just pick a topic. So we can, take out a sheet of paper, just write down who you want to work with and put like 3 topics that you're thinking about. And obviously you don't have to stay with those, but just let's make this like the official kickoff of the project so that it's been assigned now and you guys are working. Make sense? Any questions? So what you have to do with the project is we have finals week. So the week before finals, that Tuesday, everyone needs to come up here and present their topic. Okay, so you need to talk about, what you're doing related to cryptography. Let's say you're doing Shor's algorithm, so you talk about what it's for, how it works a little bit, and then you need to do a demo of some kind. But obviously today I'm going to demo how to use it, so it would have to be a little bit different from this. Make sense? And the only need is that it should be crypto related to cryptography. If you do something like Bitcoin, it has to be about the algorithms and the technical aspects and not like how to invest in Bitcoin, right? Make sense? But yeah, so that's it. Any questions about that? All right, so yeah, go ahead. Do you have a question? No. All right. Yeah, so do that actually, since while the VM is loading, you can just see if you take this opportunity to form your groups. Take a few minutes, 5 minutes or so, think about the topics that you want to do, write them down on a sheet of paper, and when you're done, just give me a, bring it up here and I'll take a look. Okay. So this is something you have to do outside of class. So I'm not going to be able to give you time to do that in class unless it's like the week before the presentations, maybe a little bit. Yeah, go ahead. What? No, it's 10% of your grade, so it doesn't have to be a huge project, right? So but just pick a topic. So I may have some ideas in Brightspace. So let's see. So let's take a look here. What you can do. Let's see if I wrote them down here. Yeah, so here's some thoughts, but you can select something else. So select a topic related to cryptography of your choosing. You will need to research and present this at the end of the semester. You need to discuss the topic and do a demo. The demo can be based on code or an application, such as in Linux. So it doesn't have to be something that you code, right? Although you can, if you want to implement Shore's algorithm from scratch or something like that, you can. But otherwise, it could just be some tool that you installed in Linux, right? And as I said, the only requirement is that it has to be about cryptography. So some ideas here. Break a cipher such as RSA and AES in a new way, though, something interesting, right? Not the things that I demo in class. What is quantum-ready cryptography? So you can explore that topic in more depth, which I think I've mentioned. I did give you an introductory article to that, right? And I've said it's when quantum computers become a thing. So for instance, there's in the news this week, you may have seen like yesterday, Google claimed that they had created a new algorithm or something that's more, that works, that solves a problem. And some analysts have looked at that and it's great as a research project, but that's still not a quantum computer. Do you see that? So that's kind of where we are. But people are already worried about when quantum computers are invented, what's going to happen, because as we will see today, we should be able to break RSA with it. And so you can explore that topic, other topics, blockchain and crypto, if you discuss the algorithms, which is what I was saying, not crypto investing or mining of cryptography, things like that. Diffie-Hellman, I covered Diffie-Hellman, but you can explore that in more depth. Certainly elliptic curves, there's a lot there. I'm going to cover it and then at some point later in the semester. It's a very interesting topic, but you can there's a lot of implementations of elliptic curves. There's a lot of research that goes into secure elliptic curves. Some are secure, some aren't. But just it's going to be like RSA essentially. It's a key exchange technique. Vulnerabilities in cryptography. There's a lot there that you can explore, right? So other vulnerabilities, other concerns. So these are some of the ideas, but it can be anything that you want as long as it's related to cryptography. Does this make sense, guys? Any other questions? Is the length of it clear now? Yeah. Yeah, so like I said, it's just, I'm not asking for a huge project, and that's why I usually just assign like 10% of your grade. But it's an opportunity for us to explore what's out there, like new things, and I'm always keeping an eye on what's going on with this quantum thing because that could certainly change a lot. Okay? All right, great. So I assume there's no more questions on the project. So just make sure before the end of class today, form your groups, 2 or 3, put like 2 to 3 topics, think about it, and then just give me a paper copy, just so I have some, so I know that you guys are working on it, essentially. All right, so I think we can move on to the next topic. So we're going to go into the virtual machine, which should be on now. And this example is very simple. I'm not going to assign a homework or anything like that. Just keep in mind, I could use this on the scavenger hunt. There may be a case where I just decide the way to do it is to break it through the quantum computer. But this should be straightforward. So let's go ahead and try it out. Okay, so the first thing we're going to have to do is we're going to need some libraries for this. So remember, so the idea is, you're breaking RSA. It's just like the lecture on Tuesday, right? Factorization is the key. Somebody grabs n and they need to factorize it into the two prime numbers. Okay, so there's going to be, so in our example on Tuesday, we used a database. Basically, people have, it's like they're brute forcing things and then they're collecting the data, loaded a database so that you can look up the answers. Okay. But there's other alternatives to doing this, such as Shor's algorithm that was, invented by a person named Shor, and it is an algorithm that is implemented on a quantum computer. So we have a library, a nice library called the qiskit. So Qiskit. And that is, and there's several libraries out there. Penny Lane is another one. And Penny Lane is also very powerful. I think Qiskit is more focused on like a quantum computer simulation, and then Qiskit is more like developing algorithms. I believe Qiskit was invented, as I said, by IBM, and it's a very well-known library in that field of quantum computing. So what we're going to do is we're just going to use it. You're not even you're not designing the algorithm. You're the IT person that manages the Qiskit computer, and so you're just going to use it, right, to try to break n, factorize n, the modulus. So the first thing we need to do is make sure that we can install Qiskit. So I may or may not have it here. So let's see. Okay, so I don't have it, so I'm also going to have to install it. I'm going to do pip install Qiskit. All right, so it finished installing. Remember, I'm using the Anaconda environment that we configured a couple of weeks ago. Okay, so again, all I did is I typed pip install Qiskit. Okay, any questions about any of this? No? All right, good. Uh, we are going to need a few other libraries, possibly like math, random. We usually use random, NumPy possibly. But anyway, let's start. We know we have Qiskit available, so let's start thinking about this algorithm. And the code is long, so the implementation of this. So I'm just gonna use it's already posted on my GitHub, so I'm just gonna copy it from there. As I said, I'm not getting into the details of how Qiskit works. But if you guys want to explore this also as a term project, as long as it's related to cryptography, that might be a fun thing for you to do. Okay. I'm just showing you really quickly how this works, and we're going to run it as a quantum computer that we have available, right? So that we can try to factorize a number. So let's go ahead and open the GitHub and find the script. Okay, so let's just go to the GitHub here. Okay, and find the cryptography repo. Okay, so cryptography. Okay, here we are. So you'll see that I have this folder in here called Crypto and Quantum. So you can click on that one, and that should have the code. So we're just going to use it as is. So now click on this one, quantum computing, and this will take you to this folder, crypto, and we can use either one of these scripts, I think. I'll use the Jupyter Notebook one. Actually, this has a nice visualization. So let's do the following. We've already installed pip. Let's also try to install Jupyter Notebook just so that we can visualize it a little bit better. So let's do pip install Jupyter. Do you guys see this like this? You may have used Jupyter Notebooks before in other courses, right? So go ahead and enter. Okay, so that did that. So then let's do Jupyter Notebook. Okay, so this actually did this. My computer. It's really interesting. Okay, so let's just create a notebook here. So let's go to fall 2025, RSA probably. Okay, and let's create new Python 3. Okay, everyone with me so far? Yeah. All right. So now, as I said, it's just so I did all of this just so that we could see the visualization, which is really nice, actually. Um, and so let's go ahead now and just use the code from the repo. So now, yeah, let's use this one. Mhm. Very well. Well, let's use the other one. Okay, so this one, let's try the libraries first. Make sure we have all the libraries. So copy these. Okay, so we had installed qiskit already. Saying can import register. Let's try that again. Okay, so that went through. Let's see what happens here. All right, so let's try the next line. Okay. No attributing it. Okay. And copy this function here. See. So I'm really just copying the whole code. I'm not going into the details of the algorithm. Then Shore's breaker. Then should be these lines. Okay, so we would need a number, which is the n. Three, two, three, 3, 2, 3, 3. Okay, so this would be the end that we want to try. Okay, and it gave an error. Rand end is not defined. From random import rand int. Three, 2, 3, 3. GCD is not defined. Okay. From math import GCD, comma, law. Okay. Try that again. So it did do something. It says that it's 2 and 1611. Whoop. Oh, okay. So I wrote 3222. That's not the number I meant to write. So you can see it actually factorize something. Let's run this one again. It's actually 3233. Ah, name execute is not defined. Okay. All right, so I'm suspecting is something to do with the version here. So let me try a different version. So let's go back to the terminal, kill this. Um, let's do conda create. Let's do clear. Conda create dash dash name pi 37 qiskit Python. Let's try 3.7. If you guys are reading online and find what version works best with qiskit, let me know. I'm guessing 3.7 might be a good one. I think we have 3.9 by default, though. I'm just changing the Anaconda environment. Okay, hit yes here. Okay, so now, okay, so let's activate this environment. So I'm going to change base to Pi 37 qiskit so that hopefully we need to find the correct set of libraries. So let's do conda activate Pi 37 qiskit. All right, so we are now in this base has changed to Pi 37 qiskit, which means we are now in that environment. Python should be 3.7 in this one. You can see it says 3.716. Okay, so all we need to install here is Jupyter Notebook first. So pip install Jupyter. Let's give it a second. Well, Okay, let's do clear. So we should have Jupyter Notebook now. Okay, so I think we were in desktop and we were in full 2025. RSA, and it's this one untitled. Okay, so let's try again. Oh, yeah, so we were using 3.9 for sure here. This one won't have it, so we need to install these. Pip install qiskit. All right, so it says it finished. Let's try this. NumPy here. All right, so that, okay. Okay. All right, so slightly better results, right? Okay, so let's clear the kernel. All right, let's try it again. I'm going to run. Okay, so no errors, didn't break on the libraries. Didn't break there. Like that's the implementation. All right. Okay, so hopefully I got results. Let's see. Oh, it's still processing. Gotta give it a minute. Oh, wait, finished. Yes. All right. So there's your quantum computer. Have fun with it. All right, so this is so I said the qiskit library. The issue was to use Python 3.7. Okay, you always have to, but this is why I gave you Anaconda. So this actually worked out nicely. So as you saw with Anaconda, I can create environments. Our default environment in base is 3.9. I created a new environment, gave it a name, Py37. Qiskit, and I installed Python 3.7. And with that version, I was able to get the Qiskit library with all functionality to work. And so now that's it. So you have now a simulation of a quantum computer. I'm not going to go into the details of this, but this could be a nice term project for you guys, or look at other options. There's Shores is one of them. There's a few other things that you can explore. Look at those, quantum ready algorithms, things like that. It might be something that you want to do. It's up to you. And like I said, everyone understands obviously that quantum computing is really hard. So no one is saying that you need to master it, you know, but that's it. All right. So in this case, just to summarize, um, we brought in the Qiskit environment. As you can see, it's got all these libraries and things like that. And essentially, this is how people today, using this one or something called Penny Lane, when they want to study how to implement algorithms with quantum computers, they come here. Even though they're not building a quantum computer, they don't have to understand physics like that, but they can start to play with the ideas of how to implement algorithms. Obviously, understanding of how a computer works under the hood might be very important for these algorithms. You can see here we start the simulation, the simulator. This is the algorithm that you need to use. And the Shores breaker, you can see the name there, Shores breaker. Okay, so the algorithm itself. And then essentially all I'm doing is I enter a number, check that it's positive, and then run that number through the Shores breaker. So the number is 3233. So here, what is that 3233? It's essentially the n in the public, the modulus, right? So you're doing factorization. All this that you see here is how quantum computers represent their processing. They have something called quantum gates and things like that. So you can see if you've ever thought of a logic gate in the context of an electronics computer, then now think of these quantum gates, okay? And so that's what they're representing here visually. So you can take a look at that, which relates to the algorithm. As you saw also, it took several steps to obtain a number. And in the end, 3233 was broken to 5361. Got it? Do you guys remember the n that I gave you for the quiz? I gave you an n, right? I don't know how big this, how that may be very big for this, but it's a fun thing to try. Do you remember what the number was? Can anybody tell me? I mean, I can look it up, but you have it. No one has it. It was 22108.
Yeah.
Yeah. So that may be too big for this, right? But why not try it? So 221, and then we'll try a smaller one. 08, but 22108 3007, right? So that was the N. Um, so let's try this over here. So 221. So essentially, repeating the quiz, right? So you would take that N from the public key that you run in FactorDB, but now you would plug it into the quantum computer. So 22108 3007. Okay, 221. Right. All right, let's try that. Whoops. It's running. I've never run that number through this, so I don't know the limits of like memory. But let's give it a second. Let's see what happens. We'll process it. Still going. So that might take a long time. Any questions, thoughts? No. Not excited about quantum computers. That's fine. Anyway, a lot of students usually in the past, at the end of the semester, their project ends up being something related to quantum computers or elliptic curves or crypto, like blockchain. Anyway, I think this will take a long time. So, well, yeah. So anyway, that's kind of all I wanted to show you regarding this. I just wanted to give you the option of introducing the qiskit framework, letting you know that simulates a quantum computer, and then putting it in the context of breaking RSA, which is what we did on Tuesday. All right, so since this is, if this were, it's likely, I mean, I don't know about quantum computers exactly, but if this was an actual quantum computer, I assume it would have finished by now, right? That's kind of the the intuition, but because this is a simulation of this and this modulus is actually pretty big, it's still going. So I'm going to stop this one, and instead, I'm just going to run a much smaller one. So I think we had a few that we did. Smaller ones here. I have one here. Much smaller. So 41,567. It's slightly bigger. 4,1,567. Try that one. This should give us 190, the two prime numbers should be 197 and 211. So if you look those up on FactorDB, that should be something that you're able to get. Still going. Let's try it on FactorDB just to confirm. Mm. 5, 6, 7. Factorize 197 to 11. Yeah, so that's for the so that's how FactorDB does it. Of course, remember this is just a database of collected data. This one actually is trying to break it through an algorithm, but it's got some limitations. All right, so let's leave it running. I'm actually curious to see how long it takes. It's just one digit more than the previous one we tried. All right, so the second, so that's it as far as quantum, as far as I go with quantum computers. But you have now something available, a library. Consider this if you'd like for your term project and if you want it. All right, so the next thing that we're going to do today is we're going to once again install another library. This is going to be PyCryptoDome, and this is a library that we're going to use now to do cryptography, right, without having to write the whole algorithm. So this is basically a library. It'll allow us to go a little bit faster and actually to combine more topics. So what I will do is, this is running. I'm gonna end this video and just call it like qiskit or something, and then let's start a new one so that actually is homework. All right. So let me go ahead. I'm gonna end this video here.